platform. But first, again, we have a session of presentation before we then go to our practical together. And as I indicated yesterday, we will start here with solar drying. And I show you some examples from practice how solar drying works. And before that, we start with a very simple kind of solar drying, which is actually called sun drying. You're just spreading things in the sun, and this is an ancient technology for drying, and this is what you can see in Asian countries, very widespread in the Philippines, Indonesia, and those countries. You see here the paddy rice as it is spread along the road, because still we have a problem. Yeah, this thing is not fitting to my head somehow. Okay, you have here a nice paved road, of course, which is heating up in the sun and quite flat and no grass below, and so fine for drying beside the traffic. And if another car is coming from the other side, cars are also moving on your paddy and are thrashing it more or less. So, okay. But you see it in many varieties. Here is a concrete platform in the center of the village where people are spreading the paddy rice. You see here a pile of paddy which is later spread on the ground, and the problem is when rains are coming, because there are up to 3 harvests of rice, and this means that at least 1 or 2 are in a rainy season, and then you have to run and you have to put together the rice and cover it with a plastic film to protect it from rain. And you see also here a very interesting structure, those furrows in the rice, and you may wonder how and why. So we are increasing a bit the surface by these furrows, and this is because the rice is turned from time to time. And on the next slide you see how it's done. So people are going just through and with their feet and turning the rice. Once in this direction and next time in this direction, and this is a very nice mixing of the paddy rice. This was in Sri Lanka, and this is a mechanized version. In the Philippines, you see that people are very creative to make life easier. I like this very much here. But there are other problems beside of rain. You see there are animals also fed by the rice and also leaving their leftovers there. So it's not a very hygienic condition, and we should improve sun drying. Another version here, it's even coffee here. Some of you are interested here in coffee. This is coffee drying in Thailand. In the background we have a nice solar dryer, which we also will see later on. But the simplest way is just to spread it on the ground and to dry it over there. Okay, drying curve for sun drying. You see here the moisture content of the product. It's an example of coffee here that started quite high here, more than 40%, and then it's somehow going down. Somehow, because you can recognize the nights. This is a night and this is a night, coming down to 12%, and then remoisten again during the night, going down, up and down, up and down. And you see this here is around the equilibrium moisture content. Here we have equilibrium with the surrounding atmosphere, and this is what we are learning tomorrow, day after tomorrow. Sorption isotherms, and why we cannot go below here these conditions. Not bad, but you see during the night there is no drying, and it takes here 3 days until we are reaching the target moisture content. What are the heat fluxes in this very simple kind of drying? We have here the ground, that might be a concrete platform in best case, but also could be just earth ground, or even grass. Then you could also have moisture from below. That's on my next slide. Here we are talking about heat fluxes, and you see there is also a certain exchange with this platform. Might be heated up during the day, you put your material on it, and then it's heating. Yeah. On the other hand, the hot material also can be cooled when there is a heat flow here to a cooled platform in the early morning. So then we have the solar radiation. This is a driving force for sun drying. Solar radiation with some reflection. And this depends on the properties of the material. Which properties of the material reflection will depend to wake you up in the early morning. What kind of property of the material do I talk about? Yep, that might be coffee or rice. The water content is one proposal. Color. Okay, there is one proposal, color. The other ones, what would you say? What is here the physical property which is here active in reflection? Why do we have reflection of sunlight, of solar energy? Which property? We have here two offers, moisture content or color. What would you say? What would you take if you would like to catch solar energy, to absorb solar energy, to make a collector, to heat air? Which color would you choose? Black, 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 black. Okay, seems to be an effect of color. It is, yeah. Black is actually no color. It's absorbing all sunlight. Yeah, and therefore it's black, not reflecting. We know that coffee is not black and rice is not black, so it's quite bright even, and then reflecting a part of the solar radiation, and this is also called albedo. We will talk about this later, albedo. Okay, another heat flux here is heat radiation. This paddy will heat up, will rise temperature, and then we have heat radiation. And this is a function temperature power 4. Yeah? The hotter the material, the more radiation we have to space. Then we have here a very interesting phenomenon. This is heat of evaporation. What will this mean? As a heat flux, heat of evaporation, what will happen there when the rice is drying, coming on the platform with 35% moisture content? Water vapor. Yeah, this is the heat of evaporation. So the water is evaporating. This takes energy, 2,500 kilojoule per kilogram. We will learn tomorrow. And this energy is taken here from the surrounding air and from the material. So that's cooling down here. This is cooling down here the material. On the other hand, there could be heat of condensation. That's just the other process. And this is happening when water is condensating somewhere. Yeah? Then the heat is set free again. Yeah? And this can happen during the night. Yeah, during the night, we have very high humidity, like here in Costa Rica, can be 90% and more. You have heat radiation also during the night, so the material is radiating to space, cooling down below surrounding temperature, and then we have here the effect of heat condensation. Yeah. That's not wanted, of course. We want to dry, but you have seen in the slide, and I go back again, that it really is happening also in practice, yeah? That we have here this remoistening. This is by condensation. So the humidity from the air is condensating in our product, and the moisture content here is rising. Okay, good. Those are the processes here which are involved here in this simple sun drying. What about the material fluxes, the water which is removed? Again, we have here our platform, and let it be coffee on the platform. Okay, there might be rain, fog, and dew. Again, not wanted, of course. We would like to prevent our product from rain. That's maybe somehow easy. We can cover it during rain with a plastic film, but fog and dew is more difficult. So if we have a very high moisture in the air, we have no chance. Then here the water will also be absorbed by our material. There even could be drainage in for some products. This is also wanted even. If we are drying, for example, grapes, they are dipped in a water solution here and then spread on the ground, and they are really wet with water, and we need some drainage that this water can drain down here to the ground. What else do we have? We have here evaporation. This is what we want. We want to evaporate the water, bringing the water from our material in the air. This is here the main process which we want, but there also could be here evapotranspiration from the ground. If we spread the material on grassland, for example, then this grassland is evaporating water. This is more than we might think. Yeah? And this water also will reach the product. So it's very good to have here a concrete platform or a plastic film where we spread the material for sun drying. And there can be absorption and desorption. Desorption is what we want, so that the product is drying and the water goes to the air, but there also could be absorption, that water from the air is absorbed by the material during night, as we have seen. Okay, those are the physical effects here during sun drying. Okay, but our topic is solar drying. And this, okay, question.
Is cement completely sealed? Or is there any drainage from cement and evapotranspiration?
No, it's sealed normally. It's just a normal concrete floor like here, concrete floor, and that's all. Yeah, there might be some fissures also, yeah, and then there might be some exchange, but normally we consider it as a sealed area. Yeah. Okay, so we are now coming to our topic, and those are solar dryers. And I have here a systematic here, yeah, how we can distinguish between different types of solar dryers. And you see here some on the left here, everything on the left are dryers with natural convection, and here on the right we have dryers with forced convection. Yeah? Here on the right, those are with forced convection. What does this mean? Forced convection means that we have fans. You see here fan. They are ventilators or fans, and they are pushing the air through our drying material. So this is forced ventilation or forced convection. Those are the more sophisticated dryers here. And on the left we have dryers with natural convection. Because if you heat air, the density will rise or drop. What? If we are heating the air, what about the density? What about air density? Higher or lower? When we heat the air, what? The density goes up when we heat it. Different opinions? Lower. Okay, lower. Will be lower. Density, yeah, okay. Density is lower and therefore it is rising. This is what you mean. Perfect question. Now it comes to humidity. When humidity is higher, what about the density of the moist air? Higher or lower? Higher density? Who agrees? If we have more water in the air, higher relative moisture content, higher moisture content in the air, what about the density of the air? Higher or lower? Higher? Yeah, raise your hand. Who means higher? Who means lower? Who has no opinion? Quite a few of you. And it's very astonishing. The density is lower. The density of moist air, of humid air, is lower. And tomorrow you will see why in psychrometrics. But this is really the 100% answer of all people. Because water is 1,000 times heavier, has 1,000 times higher density than air, and therefore we have the impression, oh, If there is water in the air must be heavier. The density must rise, but water vapor has a lower density than dry air. And that's the reason why the density of moist air is even lower. Interesting for tomorrow, but was a pleasure to have it today. Okay, so we have here two reasons that the air is rising. Yeah, so there is a add of water and of course temperature. So, yes. When the density is lower, yeah, the air will rise. If the density is lower than the air package beside, the ambient air, then it will go up. Like you in the water, yeah, you will float. Okay. So now we have here the left side, the more simple dryers. And you see another line, this one here. So we are distincting here those open air dryers. You just put them somewhere in the open. Yeah, you put them somewhere. And below this line you have the structure integrated dryers or walk-in dryers. Those dryers are small houses themselves. You can go inside. Kind of special sheds which you are using for drying. Okay, you see here the very simple ones here in this corner, and most people who are starting with solar drying, they start in this corner, and many of them fail somehow. And I show you an example of this one here. Yeah, on the left hand you see the very simplest one, just a kind of tent over it. Yeah, not bad, quite cheap. Yeah, and if you can roll it down in rain, in cases of rain, I would say very good. If you dry coffee on a platform and you have those small tents available where you can pull down the plastic film when it's starting to rain, good system. But those are the more typical when people start with solar drying, building those cabinets and using this natural convection. Yeah, here this air duct is inclined and in most cases transparent on the top and black on the bottom, used as a collector. The air is heating up inside here and then it shall flow through the material and escaping on the top. Looks very logic. I see you are enthusiastic already. And this is the reason why so many people are starting with this kind of solar drying. Yeah, having the absorber, transparent cover, and here trays with the material, here even a chimney, improving the effect, yeah, because the air is already cooler here. The air temperature is going down from the bottom to the top, and then you have here a big difference between the density here in the chimney and outside, and so the air should be sucked through. Nice idea. Works perfectly when the dryer is empty. And does not work when you bring in here the trays, because those trays are blocking the channel and it requires much more pressure than provided by natural convection. And this is a bit the fate of those very nice solar cabinet dryers, and you can see them all around the world. Even our type. Hohenheim, I would say maybe 30 years ago, when I was a master student in Greece, on Crete Island. We have been drying grapes for raisins in different types of dryers, and this was one of them here, the cabinet dryer. You see the same setup here, the collector here, the cabinet behind, and it worked fine until we have put in here the trays with our grapes, and then nothing happened. Yeah, just being heated and a bit of air exchange, and there was not a real good drying. The same thing you see here and here and here in all varieties. Here completely black, yeah, to absorb all solar energy. Here even 2 solar collectors here. Okay, nice for playing around, but for real production not so suitable. And we go a step ahead. with other simple dryers here. I will show you structure integrated dryers in a very simple setup here. Just those greenhouses, plastic film greenhouse, tobacco inside, yeah, and this is used without a fan, yeah, just waiting until the tobacco is dry. You can open here some openings to have a little bit exchange of air. Yeah, works somehow, but would be also better to have some ventilators. Yeah. And you see we are here distincting between direct drying and indirect drying. Direct drying means when the product is absorber itself, yeah, when the sun is shining on the product, like in sun drying. And it is really a good effect. Yeah? When the sun is really reaching the product as an absorber, it's really heated up quite effectively. Yeah? You have seen tobacco drying that was transparent, and then the sun reached the material and heated up the material. But there are also those barns, more typically for tobacco, even in Germany. We have those barns here. Yeah, in Germany they are from wood, and here are openings here so that the wind can pass and the tobacco can dry inside. But I show you here pictures from Egypt, where I have been recently, maybe 2 years ago, and people are drying in those shades here basil quite nicely. It's a very valuable product, medicinal plant or herb, basil. And you see many people are involved, and they are putting here the basil on those steel rods, and then they are hanging the steel rods in those ricks. Yeah, filling here everything, yeah, and you have a shade around so that there is a certain sun protection. They are not absolutely black. Some light is shining through, wind can come through, but you see there is a lot of material inside, very dense. This is now dried. Yeah, takes quite a long time, and also air exchange is somehow missing. Yeah, so the humidity of the air is very high inside because the exchange is low. So it can escape. You see it's a net, it's not airtight. There is a certain air exchange, but not very effectively. Yeah, yeah, they do it intuitively, but the heat is outside. Maybe better seen here. Look, see, it is heating up the top and the sides, so it also could be white. Black is what they just get in the market. Yeah, so a white one would be not much worse. Yeah, here it's a bit better because at least the roof and the sides are heated up by the sun, a bit more than with a white material. But believe me, a white material in Egypt is not long white, and the black one is also not long black. After a while, both is brown, because we have such a dust load in the atmosphere, and then the dust is covering the structure, and it all has the same color. I tell this because it's also our problem when we have then high-level absorbers, air ducts, with a nice black absorber. You even can have selective absorbers, a very expensive material. They are black in the shortwave radiation region, and they have a very low reflectance in the long wave radiation region. So they are really perfect absorbers, but after a while they are covered with dust and they are losing these properties. They are not longer deep dark, and they are not longer selective. They are not longer with a low emission in the long wave radiation. Okay, so you see here such examples here, but it works. Yeah, they are happy with it. They are working with it. My recommendation was then to bring in some air ducts and connecting some fans and exchanging the air, pushing the air, pushing fresh air in this shade. Okay, but now we are coming here to those dryers here, dryers which you can place in the open space here and which have here forced convection, now using ventilators. And well-structured solar air heaters. Here you see the system of an air heater. Yeah, the airflow is going through. Yeah, follow my beamer here. It's going at the moment from the right to the left here. This is the air which we want to heat up here, yeah, the useful energy. And what is the typical structure? We have down on the bottom here an absorber, a black absorber to absorb as much solar energy as possible. But this absorber will be quite hot. Yeah, can be 60 degrees and more in a good radiation. Here in Costa Rica, if you have full radiation, maybe even 70, 80 degrees centigrade. That means you also have some heat losses here on the back of the absorber, yeah, by heat conduction to the ground. If you lay it out on the ground, the heat will be conducted in the ground. Therefore, you should have here a heat insulation. Yeah, insulating material in the easiest way could be straw, or then more sophisticated insulation materials. Okay, so what's happening here with our absorber here? We have also here long wave radiation, because you have a high temperature, and you remember heat radiation is a function temperature power 4, so a lot of energy can be lost here. But we have here a cover, a transparent cover, yeah, and therefore there is also here some reflection of this long wave heat radiation, the greenhouse effect. Okay, but let's come here to our solar radiation. This is the driving force. Okay, solar radiation is coming in here through the transparent cover, but quite a bit is already reflected at the cover. Might be glass or plastic film, nicely transparent, but there is reflection, and if the inclination is even very low, yeah, in the morning, in the evening, yeah, many of the radiation can be reflected. Okay, good part is going through, reaching our absorber, and some is even here reflected at the absorber. Absorbers also are not perfectly black. Yeah? At least after a while there is some dust, and then we have here some reflection of the solar radiation. A bit wood can be reflected back here in the cover foil. Yeah, and then we have here convection. Also our cover foil is heated up, and this heat can be removed by convection by wind. Yeah, wind is blowing over it and taking away a good part of our energy. Okay, but what about the air we want to heat? Yeah, luckily the air is taking up the heat from the absorber by convection. Yeah, airflow over the absorber takes up the heat, but again is losing some of the heat again by convection here at the cover of the collector. Good. Okay, those are the processes which are going on in a collector, and this might be air or water. Collector for water has the same principle. Yeah? So sometimes we just call it the fluid, might be air or water. Fine. Okay, and what I told you about the absorbers, we want to have it black as possible to have low reflection, and here we would like to have a low long wave radiation, and there are those selective absorbers, very expensive, which have a low emittance in the long wave radiation, in the heat radiation. Okay, fine so far. We can now look at those dryers. This is the typical Hohenheim solar tunnel dryer, which I talked yesterday about. This is the archetype. Yesterday we have seen a low-cost version. This is a typical one here. It's a steel construction, yeah, set on those poles like a table, and you see the photovoltaic array and the fans you cannot see. They are here in the bottom, integrated in the bottom here. And the first part of the dryer until here is the collector. You see a transparent material, and also here you see the dust load on top of it. Even Thailand, not Egypt, where we have more rains. And below is a black surface where the air is heated, and the part here at the end is the dryer. Again, a transparent cover, and you can open the transparent cover and you can spread the material for drying. We see this more schematically here. Here the first part is our collector here, and then the dryer is starting here at the end of it. And we see a system here. It's a coiling shaft or a crank. Yeah, you can wrap it up here, and then you have access to the product to handle it. And it's a kit. Yeah, you can buy it in a box here. You see the steel frames here, right and left, and you see those nice blades here. They are filled with polyurethane. You see it here. Yeah, this yellow material covered by steel blades, like a cool house. Yeah, this material, at least in Europe, can be bought everywhere because it's typical material, standard material to build those cool houses and cool cells. Okay, so you can buy such a set, and then you can here mount it here together. You see it now half ready. You see the plates here, one blade, next blade, and so on, here holding position by the steel frames, left and right. And here we have a ridge here, which is later on holding the cover foil. Now it's painted black. Yeah, there are steel blades which are now painted here to have our nice black absorber. And then it's covered by plastic film. And it's ready for being operated. And now we see some data. Example from Sudan. You see here time of day from morning 6 to afternoon 6 o'clock, and the temperature. We see here ambient temperature here reaching nearly 40 degrees centigrade, very hot there in Sudan here in this time of the year. And then you see the temperature here at the outlet here. Yeah, one curve, second curve. One is going, let's say, to 70 degree, the other one to 60 degree. And what is the difference between the two curves? Why are they different? Why can we have either 70 degrees centigrade or 60 degrees centigrade? The airflow. The difference is the airflow. Very well observed. Here, this V stands for volume of the fluid. In our case, it is air. And here on top, it's 600, and below, it's 900 cubic meter per hour of air, what we are pushing through. Quite logic. Yeah? If we push through more air, we have a higher cooling effect on the absorber. Yeah? And the energy we are gaining is the temperature rise, yeah, from ambient or from inlet temperature to outlet temperature times the volume. And either you can have a large volume with a lower temperature or a lower volume with a higher temperature. This is a trade-off, which is later very interesting, yeah, for control the whole thing. Yeah. And what is also very important to know is this fluctuating temperature. We don't have now a uniform temperature as we have in an industrial dryer. Yeah, you set it to 60 degrees centigrade, and then you have, hopefully, 60 degrees centigrade all the time. But here, you always have this fluctuation, starting in the morning with ambient temperature. Yeah, sun is just rising here, not much solar energy. And then it's going up, and then going down again. And during night, there is no energy available. Yeah, we have to wait for the next day. And this temperature could be too high, of course. Yeah, if you are drying products here, this 70 degree is too high for many of those products. Yeah, if there is sugar inside, you have caramelization, yeah, and then the quality of your product is spoiled by overheating. That's important. What to do? If you look at this chart, you can see what to do? Yeah, more airflow. So airflow is a good means to regulate the temperature of a solar dryer. All other things are quite difficult. You could shade it a bit, yeah, but then you have to run outside and put some shade on your dryer and those things. Here, the airflow can be controlled by an intelligent control system. And those are the challenges in solar drying. This makes it interesting, yeah, to develop those control systems to keep optimal temperature. Yeah, and this temperature rise here is a function of solar radiation. This is another chart here, solar radiation here going up to 1,000 watt per square meter. And this is what we are doing later on in our practical here. This is a quite typical figure here. So solar radiation in those locations are maximum around 1,000 watt per square meter. 1 kilowatt per 1 square meter. This is what you can collect by solar energy. Yeah, so after an hour, this would be 1 kilowatt hour per square meter. What is the energy contents of 1 liter of diesel or benzene or oil, roughly? Any idea? Energy content of those fossil fuels? It's 10 kilowatt hours per liter. Yeah, 1 liter of diesel, round about 10 kilowatt hours. And here with solar energy, we have an energy offer of the sun of 1 kilowatt hour per square meter if you put it there for 1 hour. Okay, coming back to our two conditions, I have here 900 cubic per hour airflow, I have 600 cubic per hour airflow, and you see it's a linear function here. The more radiation we have, yeah, the higher can be here the temperature rise, yeah, to ambient. And we see here, it's at full noon here, at high noon, at full radiation, I see 25 degrees centigrade for 900 and more than 30 degrees centigrade, yeah, for 600. And if it's already 40 degree outside, yeah, plus the 30, then we have 70 degree centigrade. So now we are operating such a dryer with onion slices, again in Sudan. And you see a chart over the length of our dryer. In that case, it was 15-meter long. And the length is variable. Yeah, you can have longer ones and shorter ones. So more typical would be one with 20-meter length, 2-meter wide, to give you an impression of the size of these dryers. So, and we have here a line, until the line we have the solar air heater, yeah, 7.5 meter. Half of the length is solar air heater and the other half of the length is our solar dryer. And we see the temperature versus the length of our solar dryer. And you see it's rising here over the length, yeah, accumulating heat, yeah, taking the heat from the absorber. And if the dryer is empty, then this continues. Yeah? This is the empty dryer, just continues. Do you have any idea why this is not just a line, a straight line? Why is this such a bowed curve? Can you please repeat? Yeah, there is something like a maximum. So by physics, just by adding here meter for meter in my system, I would also gain more and more energy, and this would be a line. But I'm rising temperature, which each meter or each millimeter, I'm rising the temperature, and then my losses to ambient will increase, because the losses are a function of the temperature difference. Yeah, the higher difference, the higher the losses, and therefore here my losses are increasing, and I even have here a stagnation. Yeah? A stagnation, because then the additional energy gain is just again lost by the very high temperature difference to the ambient. Okay, so we are even talking of a stagnation temperature in absorbers, in collectors, sorry. Good, this was our empty dryer. And now I have a dryer which is just filled with onion slices, and they have a moisture content of 75%. So onion slice is very wet, and I put it inside. Again, a product where I would like to have some drainage. They are washed after cutting to wash off the sugar from the surface, and then I like to have a bit drainage on the ground inside the dryer. Okay. So what's happening? In our collector, I have the same curve here, because nothing happens with a solar air heater. But then I am reaching here my dryer, and this dryer just has been filled with my wet onions. And now I see that the temperature is not rising, but is decreasing. Why is now the temperature decreasing in my dryer? Absorbing heat, evaporating. Now we start to evaporate. Water is evaporating from my onions here, and this needs energy, and this energy is taken from the air. This is the heat of evaporation. Okay, therefore it's going down. Then we are coming to close to the end of drying, moisture content of 10%, and you see here it's still heating, but not so much as an empty dryer, because still some water is evaporating. It's so hot in this dryer that we can go below 10%. Yeah? Equilibrium, I estimate, for this temperature will be around 3 or 4%, and therefore there is still some drying here. And the other reason might be that the onions are quite bright. Yeah? They are quite white and have a high albedo, a high reflection of the sunlight. They are not good absorbers. This is an additional reason that we don't reach here the temperature of an empty dryer. What about the relative humidity inside my system? Starts with 60%. This is ambient relative humidity in Sudan in this day. And then I see that the relative humidity is going down in my solar air heater. Why that? Why is relative humidity going down in the air heater? What's happening there? Temperature. Exactly that. Nothing is happening in terms of absolute humidity. There is no water absorbed here, but the temperature is rising, and therefore the air can take more water, and therefore the relative humidity is declining. Psychrometrics tomorrow. We can calculate here how the relative humidity is decreasing when temperature is increasing. Okay, not astonishing. And for the empty dryer, it just continues, but not here for the filled dryer. You see the line for 75% here. Yeah, and this line here is somehow stagnating, and this is fine. Yeah, because if it would go high here, then the drying process would be hampered. Yeah? So we have enough air to keep it more or less constant, yeah, to push away here the humidity which is now evaporating from our onions. Okay, good. So now we are coming to banana in Thailand here, using a similar dryer. I think this one is now longer, 20 meters long. You have seen the picture of this solar dryer some minutes ago. And we see now here a chart, the moisture content of those bananas here over time, and the time in days. 1, 2, 3, up to 5 days here. And we are comparing sun drying, those are the white symbols here, with the solar tunnel dryer, the black ones, and you see again those steps. We have seen it already. Typical line for solar drying. We have drying during day and we have stagnation during night. Same game here. Okay. And in this case, we need here 3.5 days for the solar dryer, tunnel dryer, and we need close to the 5 days here for the sun drying. In this case, because we can raise the temperature in our solar dryer more than in the ambient, and we have a more effective drying. You see here the drying rate, how many water is removed per time. It's high at the beginning and is then decreasing. The drier the product, the lower is the drying speed. The water cannot escape so quick in a more dried product. And this is what we will deal with in the last day in drying kinetics. Also very well known, that from a fresh product here, water is escaping much quicker than here from an almost dry product. So, and this stagnation during night is of course not very nice. And so we also tried to find solutions. We have here a type where we have the collector on the right. This is our solar air heater here. The air is turned around behind and then coming back through the dryer zone. Here on the left is now our dryer. And in this area where the air is turned around, we have a biomass heating system. And this can be then heated during the night. And the air is heated here and we can continue with drying. You see a cross-section of the biomass heating system. Here a steel plate, and we have here our furnace. You can feed it with solid fuel, with wood, and gases are going inside this chamber, heating the metal sheet here, and then the exhaust gases are leaving the system by a chimney. It works, okay, but you see these drawings are very old. That was at the beginning of our work there when I still was a student, so 30 years ago. And we showed it works, we can do it, but it was not economic. If you have here such a furnace, then you also could put it somewhere inside a building and could have a regular dryer and being rid of all the problems with solar energy. Am I right that we have now a break, or you don't know? Maybe you can look what they have prepared so that we don't miss our break. Okay. Makes it complicated, and was not continued then. And this you have seen yesterday, So this very nice version with steel and this polyurethane plates, very nice to have, and it's sold worldwide. There is a spin-out company from Hohenheim that was founded 20 years ago, Dr. Esper, who is now commercializing this dryer, and really in many, many countries worldwide, and still there are offers, and still it's sold. And it's very fine for those high value products. But then also a company tried to dry here those stable crops, low cost, maize, rice, those things, and then this type was constructed. And most of you have seen this yesterday, but we have some new people here. It's just a tube, plastic film tube, transparent on top, black on the bottom, closed with a zipper here. The fans operated by photovoltaics, though you can operate it also outside the village. Here in the village you might have electricity if you are happy, but you also could operate it at the border of your field. And there was a video which I also will show again. This didn't work here. You see, the two people here are pulling here the steel tube below the black plastic film, and the paddy is jumping over the pipe. And a very easy way to mix the material. If you have the regular type, you have to open the plastic film and you have to steer the material to move it. If you don't do it, you have certain areas where it's still humid, and difficult to penetrate for the air, nests with moist material, and they can start to rot. You have their microbial growth, and therefore you have to agitate the material, you have to steer it. So when we have a look inside the dryer with a thermo camera, with an infrared camera, you see that here the paddy rice is nicely heated here. It's around 50 degrees centigrade by color. You see also these areas, the black absorber is even hotter because it's black, less albedo. And this temperature might be critical, should not be too long higher than 40 degrees, otherwise rice will crack, and therefore it's so important to turn it. Like the boys did it with their shoes, in open sun drying, you also have to turn the material in solar drying, but it's now very easy with the steel pipe system which was invented by farmers in the Philippines. And then of course we make measurements here. This is the climate here in the Philippines when we used the dryer here for paddy rice. There are some rainfalls here. Those are the rainfalls from time to time in the rainy season, and in the dry season even there can be some rainfalls in the Philippines, and this is the argument for the farmers to decide for such a solar dryer instead of sun drying, because they are really tired always to look when it's raining and run and cover the material. And this is their main argument, to have a solar dryer. And here we have the temperature in the solar dryer, together with solar radiation. You see the gray curves here. This is a solar radiation fluctuating. We have here 2 days here, a day in the rainy season, a day in the dry season. We can start somewhere here 10 o'clock in the morning. You have to wait until the paddy is arriving at the dryer, and then you have some hours, but always you have some clouds, and you have here fluctuations in the radiation, and then the long night is starting. Here is night, no more temperature and no more radiation, therefore temperature is going down. We have here again a short preheating area in that case. Our philosophy is now the rice should be the absorber, but still we have 1 or 2 meter preheating with a black bottom material, and then the air is pushed over the rice. Temperatures are then going down here during the night, also in the dry season, and this is then the reason for stagnation. The curves here are not the absolute temperatures, of course. They are not zero in the Philippines. This is here the temperature rise, temperature rise to ambient. Here above we see the curve for ambient temperature. In the night it's 28 degrees centigrade in rainy season, and even a bit higher in the dry season. Solar radiation, you see in watt per square meter, is even exceeding a bit 1,000. Might happen, until 1,200 watt per square meter, and especially in cases when the sun is shining through clouds. You have some clouds in the air, but there are openings in the clouds, and the sun is shining through, and then we have some back reflection from the clouds. Some of the albedo of the Earth, which is reflected up in the sky, is reflected back again from the clouds, and in those cases, when the sun is shining through those holes in the clouds, we might have here very high radiation here, exceeding 1,000 watt per square meter. Yeah, and then we have here the temperature time accumulated here. How many hours do we have at which temperature? And we compared here sun drying with our solar drying. ISD is our inflatable solar dryer, which you can blow up, inflatable. In the Philippines, they call it bubble dryer. We don't like this so very much. Sounds a bit funny, bubble dryer, but that's the name which it has now, worldwide, the bubble dryer. Okay, you see there is not so much difference, in the solar dryer. Here we have a bit higher temperatures for some hours here, also here in the dry season. And here under bad conditions, the line above are good conditions in rainy season and dry seasons, and this was a bad season where we have rains here in the system. Yeah, you see that there is a bit of an advantage here in the solar dryer. We have some hours where we have higher temperatures in the solar dryer. Yeah, good. But the differences are not tremendous, and this is also then shown in the drying curves. White solar dryer, black sun drying, and you see it's quite similar here. And between 12 and 14 is our target moisture content. So we have reached here 12. If we can stop here, fine, but it was not stopped but continued. Then we have here remoistening during the night here, and then drying continued in the next day. In the rainy season, in the dry season, it is quicker here. Yeah, so you could stop here even the sun drying after one day. You have reached the 12% here, yeah, and then the next day was continued, and the moisture content was even lower for sun drying. Too low, of course. Yeah, you should stop somewhere here at 12% moisture content. Good. And this shows for paddy, rice, the same for maize and so, for those stable crops, the benefits of the solar dryer are not a quicker drying, as we have seen for fruits like banana. There we really have a quicker drying. But we have this protection from rain. And this is the reason why people apply the solar dryer here for grain. Again, we have rainy season and dry season, and we have here temperature profiles, nicely done now in color here. We have the time of the day for 1, 2.5 days, and the temperature over the length of the dryer. Yeah, follow my pointer. This is the length of the dryer. Of course, temperature is rising, but not linearly, but as a duration curve here, reaching here kind of endpoint here. Yeah, good. And in the dry season, we reach much higher temperatures, too high, 70 degree closely, 60 to 70 here, and 1.5 day, even 1 day is enough for drying. Okay, now I have some pictures again from Egypt. There they are drying medicinal plants in certain boxes. You see it in the next slide. In our typical solar dryers, we push the air through. Okay, but in these dryers, we can suck it through. So we have here the stacked boxes, here a high stack of boxes, here just 2 layers of boxes inside. Let me see if we can see, or better so. You see here those boxes, those trays, which they are using traditionally for drying. They are filling here peppermint inside. You see also those boxes everywhere around, and normally they just put it on stacks in the open air. And they invited me, to think about solar drying, as simple as possible. And then we decided, we are using your boxes, and we make a solar dryer from it. We put here straw on the ground, just the stalks of peppermint as a heat insulation, laying a plastic film on top of it, and then placing the trays Yeah, and we let one empty here so that we also have an airflow below the material. Then we have here a layer of material, and then we close it with a plastic film, and we have here a ventilator sucking the air through. And by suction, we are sucking the air on the boxes. And this keeps the whole thing together. So you don't need any other structures, yeah, just the under pressure, and the plastic film is keeping together the stack. And the same we made here with multi-layers, many layers of boxes here. Maybe now I can go back again. Yeah, you see here the big stack and the small stack here, and you see the foil is sucked in. Yeah, it's running already. Air is sucked in here and blown out here. Yeah, and this is a system from top. Also, again, we had here the first area as a collector, heating the air and then blowing here over the material. Top view, side view, we have here the many boxes here stacked one upon the other, and we have here our absorber in the collector area. We put the absorber somewhere here in the middle. Yes? Yeah, of course we make calculations. Yeah, in that case we just choose a quite big one to be sure that we have enough pressure available for the airflow we want to have. Yeah, it's a question about the airflow. We know how much air we want. You remember the 600 cubic meter or the 900 cubic meter for the other dryer. So we know the air exchange rate we want to have to remove the water. And if you know the airflow, then you have to know the pressure drop. And this is something which you have to estimate or calculate, the pressure drop, and then you can select a fan according the characteristic line of a fan. We make calculations. I even have, again, an Excel practical for fan selection, which I did not include this time. Yeah. Yeah. No. No, here you have just to estimate. Yeah, you can calculate for an open channel. Yeah, you know the cross section, and this is in tables or in equations. We don't use tables any longer. We have those things in equations. Yeah, and you can calculate here the pressure loss in the air duct, and then you make estimations. Okay, how much will be the resistance of the material? And of course, you are gathering experience. Yeah, if you work with certain materials, you know about the range of resistance of those materials. And air resistance here is, I think, lower than you estimate. It looks quite blocked, but these medicinal plants, yeah, stalks, so it's quite bulgy with a lot of pores in between. And you see that we are, by purpose, leaving here slots. Yeah, those slots are open, and the air can flow over and under the material. Not all the material has to penetrate the layer. Yeah, because I agree, this is a quite long, this is high length here, and if you push the air just through the material here, the resistance might accumulate to quite high value here. Yeah, but you see the white spots here, the slots, there is the space for the air to over and underflow the material. Okay, but very interesting. And yeah, I even could upload, for your interest, the Excel practical for ventilator selection. Then you can calculate, not just look up in tables and make estimations. Yeah, but look, this is really a crude setup. And it was, I would say, a first start. So we made it really with almost nothing, yeah? The ventilators even have been available here, and plastic film was bought in the market, and then we could start. So, yeah. And I have seen, okay, they are strong enough to. And if the airflow is too strong, we can close a bit here the outlet, yeah, to bring down the airflow, yeah. But I show it because it's the start of new things. Now we have seen, okay, if we are working with boxes, we don't longer depend of blowing up the structure. You remember the bubble dryer? And there are also no structural elements. There is not longer here the ridge, which is covered with a plastic film. But this means during night you have to blow air in. Otherwise it will collapse. Yeah? And then the plastic film is in direct contact with the drying product, and this is not good as long as it's wet. That is fermenting, yeah, if there is no airspace. And this was a reason in the Philippines why we have re-moistened the paddy during night, because we have been forced to operate it also during the night. Of course, we did not blow the full air volume through it. We blocked the outlet and just have been blowing air inside. But again, there was enough exchange for remoistening of the material. And this brings us to new ideas. Okay, if people are accustomed to work with boxes, and many are, then we can just wrap those boxes here and suck the air through, and during night we just stop it, and nothing will happen. And this is what we are doing just now. We are building a new version here, a suction type, much nicer than this, of course. Yeah, we have done a nice frame where we put the boxes on, and we are using standardized boxes, plastic boxes, yeah, where we put then the drying material inside. Okay. Yeah, but people have been happy about it. It was really a nice experience. Yeah, after one day the material was dry. Not so in the big one here. I would not recommend to make too many layers of boxes here, but to have this version with one layer, that was perfect. Okay, we are coming here to a new category of dryers. It seems that we don't have, or we have. Coffee break? It's a perfect time because we are coming to a new topic. And so let's have a coffee together. Thank you. back again. I think we lost few, but maybe they are turning up again. So, another type here. We are here now with structure integrated dryers, but with ventilators. And this is such a greenhouse type solar dryer as you just showed me in the break for coffee. This is in Thailand, our colleagues there. And we are using their greenhouses with polycarbonate covers. They are a bit more rigid. Yeah? So it's not just a plastic film, nice greenhouses. And then there are tables inside, and on the tables is the drying product, might be banana, you will see tomato in a while, and there is an air duct system. This is an air duct system bringing in the air here, which can be heated by a furnace outside. You see here a gas burner outside. The sun is shining inside, and the material itself is absorber. It's direct drying, and here by the fans here in the outlet, an exchange of air is guaranteed. Okay, this is the working principle. So during day, you can stop the gas burner and just sucking in here fresh air through the whole greenhouse, heating up, taking up water, and then escaping at the air outlet. During the night, you can start the gas burner and heat up here the system. That's how it looks like. A nice polycarbonate greenhouse, very nicely done in Thailand. Look inside. Here the trays with the tomato. You can go through it here. And you see the fans here to suck out the air. And the inlet is where we are standing on this side. Yeah, the tables with the trays. Those tomatoes, they are squeezed by purpose. They have a machine to squeeze it, to open it, and then they are dipped in osmotic solution. It's osmotic pre-drying with sugars. And in Thailand, this product is eaten as a sweetie, yeah? The tomato. Here they do it, yeah, the machine to squeeze the tomato. Here the squeezed tomatoes are collected and then here heated in this osmotic solution. Yeah, they have different types of sugar contents which they are using, even salt. You can use either salt or sugar, or even a combination of salt and sugar for osmotic pre-drying. Okay, and coming to this type here with a collector integrated here in the building, and then the dryer inside the building with a fan system, indirect drying with a forced ventilation. Also constructed from a greenhouse. From here, it's a regular greenhouse here in Germany here. And this dryer was my PhD work, by the way, and was then also produced in several countries. Inside is the dryer. I show you the system here. The roof is used as an air heater or collector. And each of these 2 meter wide fields has its own ventilator pushing the air over the roof. The roof has 2 layers, you will see in the next slide. And the air is then turned around here. And the side facing the south, this side is facing the south in Germany, is extended so that we have here a longer area in the south here. The air is heated and then guided through those so-called flatbed dryers, boxes with a perforated floor where the material is laid out here. In that case, I started with medicinal plants, drying there. And you see here a flap. At the moment, it's of fresh air mode, so fresh air is sucked from outside, heated and brought inside, escaping to the sides. And you can also close the flap, yeah, bring it here upright, closing the opening, and then the air from inside is recirculated here in the system, and you can reach much higher temperatures. So here you see a cross-section of the roof. Here we have the transparent cover. It's very good plastic film. It's an air bubble foil, and you can walk. You can really walk on the roof. You should not put on high heels, but with normal shoes, you can really go up the roof. And we have here a black tissue as absorber and another air bubble foil here on the back side here, and the air is blown through this air duct for being heated. Inside the dryer, you see the boxes here. It's always 2 meters. You can separate it, so you can dry different things at the same time if you like. But mostly, when there is harvest for a special product, we can remove here these walls and use the entire area here for drying. We have also similar curves for temperature. You see the ambient temperature here. This was in Czechoslovakia, former Czechoslovakia, Serbia now, where we did the experiments here. And you see without recirculation we can reach here, so 45 degrees centigrade maximum during high noon. But with recirculation here we can go up above 60 if we want. And here it's again a function of solar radiation without and with recirculation. And now we have to develop here a regulation system so that we work with the flap. Should not be too high for certain medicinal plants. It should be not more than 45 degrees centigrade. And also you cannot recirculate all the time because you are also accumulating water. You are evaporating water from the material. And so you have to make this decision. You have to make an algorithm, a computer algorithm, when to open the flap. You see here the drying here, with recirculation here, quick drying, 4 days, and again you see here these steps, stagnation almost during the night, quick drying during the day, and temperature has a very strong effect on drying, which you will see on Friday, and therefore you always should apply the maximum allowable temperature for drying to have quick drying. Solar radiation in Czechoslovakia, could be quite high here. And you see temperature and relative humidity, they are just vice versa. Tomorrow you will see why, because relative humidity is just a function of temperature. So moisture content over time, the drying curves. Here for chamomile, you see that it also depends on the mass you bring in the dryer. I have given it here in kilograms per square meter, 15 kilogram of chamomile per square meter, 30, 45, 80. Okay, and then you have the drying curves. It depends also on the material. You find here chamomile again for 20 kilogram per square meter, compared to lemon balm, to sage, to peppermint, and you see each product has its own drying behavior. You have to make lab experiments before to predict the drying behavior of those materials. Here are some figures here. We see initial moisture content for those medicinal plants. They are in the comparable area here, around 70, 80% here. Drying time for peppermint was very long, 104 hours. The capacity is given here. The water you have to evaporate is high. There's a lot of water because we have a very high initial moisture content. And you see here the essential oil before drying and after drying. And you see that in most cases here we could keep here the essential oil content of the product. Okay, so by modeling the whole system, we can also predict the drying curves for other months here. And we also can calculate the capacity for the different products, chamomile, sage, peppermint, over the year. And the black lines are the times where there is the regular harvest of those products. And you see it's varying not only over the day, the drying behavior, but also the drying capacity is varying over the year. In our regions, we are on a high latitude, so 45 degree, you are here on 10 degree, and you will see today when we make our practical that this has a very high impact here on solar radiation over the year. Yeah, again, here the long nights without drying have been a bit frustrating, and therefore we also integrated here a heating system in the dryer. You see here the top view from this corner here, and there was a fuel burner installed, which is heating the air here, an air duct on the southern side, an air duct. This is used as air duct, and hot air is blown in here to heat the system during the night. And you see, without heating here, peppermint takes 7 days, and if we have continuous heating, then we can reduce it to 2.5 days. Of course, then we have to invest in the oil, what we are burning, but we are increasing the capacity of the greenhouse dryer tremendously. Here is a fuel consumption. You see we are consuming here by continuous heating 1.3 liter per kilogram of dried product. This is of course adding to the price of the product. Each kilogram of peppermint which we are now producing has also to pay for 1.3 liter of fuel oil. And then when I was in Egypt, I have seen this. They just copied it. So if you are publishing, people are able to copy. And we don't apply for patents. So I even was pleased to see it here. So, and they do it then in the local style. They look what's available in the market, which plastic films and so on. And they did it nicely inside the boxes here. And they are drying basil inside. You can even go between the boxes, maybe even an improvement to our type. You can go inside and then mix the material and handle it. Okay, so that was the last example here. And now it's your chance to ask questions. No questions at the moment? Yeah, there is one.
Okay, you said that airflow, you can control the temperature with airflow, right? Inside the dryer.
Yeah.
So if I saw there that the fans were in the top of the dryer.
This is true for the tunnel dryer. In the tunnel dryer, we are controlling. Yeah.
And it is important that they're in the top, not in the bottom.
I talked about the tunnel dryer, which is not high. Yeah.
But if the large one that you saw from one of the tomatoes.
The tomato. Okay. For tomato dryer, there is no need to control the temperature because it's not too high. If you increase the speed tremendously, if you would increase, but you see it's just a minimum exchange. You see, those are small fans here, and it's just enough to keep the temperature under certain limits.
And if you want to remove that most humid air, where would you put the fan?
Yeah, they are in a good place. Where should they be? They are sucking the air from this point here, across the greenhouse, and escaping here.
It doesn't matter if it's in the top or in the bottom or...
The idea is that the air also should penetrate a bit here the trays. The idea. But the air goes the way which is the easiest. I would say most air, sucked in here on this side, the most air would pass by here and go up here. So this airflow is not very much guided, so it's a bit random. Yeah. So it's a bit improved by the heating system. This is better. You see, I have here the air ducts with a very good defined airflow. It's blown under the trays, and the air is going here, through and aside the trays, and then leaving here. Okay. Yeah. Here in the inlet, you have ambient relative humidity in Thailand, and according to the season, it can be quite high in the rainy season. Again? The higher? The highest value, during daytime, it's up to 50% relative humidity, but during night, it's going up above 90. Oh, yes, because you are heating. You are heating the air inside the greenhouse. And by heating the air, you are going then below 70%. Yeah. Okay. So now we are coming to the point where we start with practicing. So I would propose that you try to enter the e-learning platform, and that you also start your laptops so that we can start to work together. So everybody should try here to enter the e-learning platform. I can search again for the link to enter. No, it works. Yeah. What happened here? Okay, you see here the link again. You have to register. If you use this link, there will be you have an access to register. It's in German language, I'm afraid. It's quite funny. And the ones who are so far, to see this site in Open Ilias, I can come and show you where you have to register. You are in, no? Seems you are in, no? Yeah. You are in, no? Oh, I think now I remove this.